So can you see the screen?
Yes, ma'am.
Okay. So last time I was telling you about baryon number conservation. That is, number of baryons in the universe remain the same. Our baryon number in the left-hand side of a process should be equal to right-hand side of a any elementary particle process. I gave you some exercises on that also. And then now, what is the baryon number of proton? If I ask you, what would be your answer? What is the baryon number of a proton?
1, ma'am.
Baryon number of a photon?
0, ma'am.
Okay. So you should get internalized what is meant by baryon number. Then people started asking questions like, if number of baryons are conserved, can number of leptons also be conserved? Can we formulate a law of lepton number conservation? That's what I'm going to talk. So now we have a formulation of our conservation of lepton number. It was introduced in 1953 by Italians, Konopinski and Mahmoud. They assigned lepton number L is equal to 1 for all leptons and lepton number L is equal to -1 for antiparticles, antileptons. What is antilepton of electron? It is E plus. Antilepton for mu minus, that is mu plus. Antilepton for a neutrino, it is nu bar. So all other particles, that is hadrons, baryons, mesons, photons, they all have L is equal to 0. For example, for a proton is a baryon, it has lepton number is equal to 0. Similarly, a baryon number of an electron is 0. So we should know these things, and then I will continue to say, fine. Conservation of leptons says that number of leptons after a process is equal to that before a process. That is, elementary particle interactions, all elementary particle interactions. How many are there? There is a strong interaction, there is a weak interaction, there is an electromagnetic interaction. All these conserve what is called as a lepton number. Lepton number on left-hand side should be equal to lepton number on right-hand side. This is stated as, in all elementary particle processes, number of leptons should remain a constant. I cannot create a lepton when there is no lepton in left-hand side. I cannot destroy a lepton when there is, that is, if there is no lepton, if there is a lepton, I can't destroy it in by a elementary particle process. For example, if I say neutron decay process, there is a neutron decaying into a proton plus an electron plus antineutrino. Now you tell me, what is the lepton number of neutron? What is the lepton number of a neutron?
0, ma'am.
Okay, left-hand side lepton number is 0. Right-hand side, what is the lepton number of proton?
0.
0. What is the lepton number for an electron?
1.
So if I didn't introduce a neutrino, left-hand side lepton number is 1. Right-hand side lepton number would have been, sorry, left-hand side would have been 0. Right-hand side would have been 1. So people said, it is not a neutrino, it should be an anti-neutrino, so that left-hand side, right-hand side neutrino number is equal to 0. Now, for example, I will ask you, if a neutron decays into a proton plus an electron plus a neutrino, what would be the lepton number of right-hand side?
2, ma'am.
So I can't have it if lepton number conservation holds. So I should introduce a new bar, so that lepton number is 0. That's why I had been telling you, we take it as new bar on right-hand side. Now I am explaining you why people took new bar instead of a new. Because all other conservation laws say you have to introduce only a neutrino. It doesn't matter whether you have anti-neutrino, neutrino, as far as other conservation law is concerned. But when I introduce a lepton number conservation law, a new conservation law, then it tells me that the neutrino has to be anti-neutrino. Otherwise, this process does not conserve lepton number. In other words, I am just telling you from my assignment of lepton number, neutron beta decay written in this particular way conserves lepton number. Lepton number L is 0 on the left hand side because neutron is not a lepton. On the right hand side, we have L is 1 for electron and L is -1 for anti-neutrino. Therefore, total L value is 0 on the right hand side too. And now let us take what we did to check whether neutrino and anti-neutrino are the same. There is a process which was experimentally tested by Davis and Harmer. I had mentioned it 2 classes earlier, I think, or last class. So the process is anti-neutrino plus a neutron gives you proton plus electron. Tell me whether this happens in nature. What is the lepton number on left hand side?
-1.
Right hand side?
+1.
So it doesn't happen. Davis and Harmer were checking this process, and you know that it did not happen, which told us that neutrino and anti-neutrino are not same particle. Suppose I put a neutrino instead of an anti-neutrino here. Instead of nu bar, if I put a nu here, then this process is okay, because lepton number on left hand side is 1, right hand side is also 1. But Davis and Harmer assumed that neutrino is its own antiparticle and then tried this reaction. It didn't work. So because if neutrino and anti-neutrino are 2 different particles with lepton number 1 and -1, I should have lepton numbers different so that I characterize, I distinguish between a neutrino and an anti-neutrino. They are not the same, is more emphasized theoretically when I put the lepton number into the relation. So now this is what is one more thing. However, law of conservation of leptons required further refinement to take into account 2 more types of neutrinos called as electron neutrino and muon neutrino. They are found in nature. I am stating it. I want to explain it in the next slides. What I am trying to say is lepton number conservation is fine. We can accept it. We will check every process that is known to us in nature and verify whether lepton number is conserved. So then I had to introduce a refinement, classification further into the conservation of lepton number. How do I do it is the next story. So for example, I take one particular process in nature, which is appearing in nature. So we have what is called as charged pion decay. See, remember, we have so many processes happening. Each process comes with a story. Remember the story, then you will be able to write the process properly. So if I take charged pion decay, this is seen in cosmic rays. That is how people first discovered muon in nature. Pion decays into a muon and something else is what is seen. That something else is a neutral particle, and in order to conserve everything, lepton number, if I check lepton number, what is lepton number? Left hand side. I write this process, then you will have to verify is lepton number, because our story today is lepton number conservation. Fine. So I will ask you what is lepton number? Pi minus, for pi minus.
0, ma'am.
It is a meson, so its lepton number is 0. It's not a lepton, so it is 0. For mu minus?
-1.
No, +1. Electron is a lepton.
+1.
Muon, same type. Muon, remember muon is a heavy electron. That's all. So electron has lepton number +1, not because -1. Muon is like a electron. Electron is our particle, lepton. So it is +1. Muon has a +1. And then I have to add something here. Otherwise, I don't have any conservation loss. I check that it has to be an anti-neutrino, because lepton number conservation gives me for mu minus it is +1. For a nu it is +1. For nu bar it is -1. 1 minus 1 is 0. It matches. So this is the process that I write in my laboratory. But what I detect is only a mu minus. I cannot detect a new bar, correct? How do I detect a new bar? Is there any way to detect a antineutrino? Is there an experimental detection for antineutrino? Yes or no? Can you detect an antineutrino experimentally? Yes or no? I
Yes,
don't.
ma'am.
That's what I have taught you, right? The Riens-Covans experiment detects antineutrino. So if I keep a source of ions, I will be able to find antineutrinos. Like how I keep neutron decaying into a proton plus an electron plus antineutrino, I will be able to use this process and check whether antineutrino is there in that Savannah River reactor. So I am just telling you some kind of stories associated with this. For your purpose, examination purpose, you are checking what is a charged pion decay and what is the associated story as far as conservation of lepton number is concerned. Lepton number left hand side is 0. Lepton number right hand side, for a mu minus, lepton number is +1. Antineutrino has a lepton number -1. So it is conserved. Lepton number is conserved according to you. Same way, I have a charged pi plus decay. Pi plus is a meson. So lepton number is 0. Right hand side, I have a mu plus. What is the lepton number of a mu plus? What is lepton number of plus, mu plus?
-1.
-1, because it is like a positron. Electron is a particle, positron is an antiparticle. Mu minus is a particle, mu plus is an antiparticle, antilepton. So this is -1. And for a nu, I will get a +1, -1 +1, 0. These two are detected in cosmic ray events, not in laboratory. Today, people discover it in laboratory also. These were first detected in cosmic ray events. These are processes. So now, cosmic rays do not detect nu bar and nu. They detect only mu minus, mu plus. Then we put in appropriate quantities so that all the conservation laws hold. So now, the muons further decay into an electron or a positron. Suppose I write mu minus, it further decays into a electron. If I write mu minus decaying into a electron, just electron, will the conservation law hold? Don't write neutrino and antineutrino. Just say a electron. What is lepton number left hand side?
1.
Right hand side?
1.
So, but this should happen in a straight line, because momentum conservation says initial momentum should be equal to final momentum. I don't find in this process electron moving in a straight line with the muon. I do find that electron goes in random directions. So I should add one more particle which is readily available to me. What do you add? You add a undetected kind of particle, neutrino. But if you add a neutrino, what do you say about lepton number? Now, lepton number on left hand side is 1. Right hand side, electron has lepton number 1. But if you add a neutrino, lepton number is 1 more, +1. 1 plus 1 is 2. Lepton number doesn't match. So you have to add an antineutrino also, so that right hand side lepton number is 0. Do you understand what I am saying? If you say mu minus decays into E minus, I find an electron in cosmic ray events, decay, mu minus decaying into electron, particle track can be detected. Charged particles moving in a photographic plate, it will leave a track. So I do see a track of an electron. Fine. I don't see anything for neutrinos. Neutral particles do not leave any track. But if I write only electron, our conservation law is like a guard for us. We have to preserve it. So if I write mu minus going to E minus, it has to happen with momentum conservation. It tells you that mu minus going to E minus should be in a straight line. If mu minus is in rest, E minus should also be in rest, kind of things. But that is not seen in nature. So experiments tell me that E minus is in arbitrary direction than the mu minus. So I will say there should be additional particles. I add a neutrino, I add an antineutrino, then right hand side, what is lepton number of right hand side is going to be 0. Electron has lepton number +1, neutrino has lepton number +1, nu bar has lepton number -1, 1 minus 1 is 0, and then I have 1. Left hand side 1, right hand side 1. This is possible. So I will write this is mu and dk is what I will say. Similarly, for mu plus, I can write the same kind of reaction. Instead of E minus, I have a E plus. Check. First reaction leads to second reaction by crossing symmetry. Correct? If you replace a particle by an antiparticle, you get this process. Correct? Do you follow what I am saying? Is that fine? I'm only
Yes, ma'am.
talking, appealing to you only about conservation laws. So please understand that these two are crossing symmetry relations. I do find this kind of processes happening. Now, I ask you other question other than what I am teaching now. What I ask you is about angular momentum conservation law. What is left-hand side angular momentum? Do you know what is the intrinsic spin of mu minus? Electron is a spin half particle. Proton is a spin half particle. Neutron is a spin half particle. Neutrino is a spin half particle. What is the spin of mu minus? I told you it is almost an electron. It is just that it is heavy.
Half.
It is spin half.
Half.
So I am talking about lepton and baryons. They are all half integral spin. Half integral means half 3/2 kind of spin. Leptons and baryons are fermions. So please remember that one thing. And mu minus is like a electron. Remember that. It is at least to remember. If not experimental values, you should remember mu minus is like a electron. Its spin is half h bar. Electron has spin half h bar. Now let us check what is the angular momentum conservation. I am just asking you because when I introduce a new process, you should know what is the corresponding angular momentum conservation law also, what is the charge conservation law also. So what is angular momentum conservation law? Left hand side is half. What is right hand side angular momentum? Electron has angular momentum. What is angular momentum of electron? Spin, I mean spin.
Half h bar.
Half. A neutrino? What is spin of a neutrino?
0 spin.
Is it a lepton? Neutrino, is it a lepton? Is neutrino a lepton?
Yes, ma'am.
So if lepton cannot be 0 spin. A lepton is a fermion. I made a statement. Every statement that I say, if it is not an error, it's weighted. That is, you have to take some, just now what I said, you have to remember. So if you say neutron is spin 0, then I will show you many processes where angular momentum does not get conserved. So neutrino has spin half. So now I will ask you about, though my talk is about lepton number conservation, I am diverting and making you sure that you learn angular momentum conservation law also in these processes. In whatever is seen in this page, I want you to know about angular momentum conservation law also. So electron is spin half, neutrino is spin half, antineutrino is also spin half. You have to make note when I say certain things, then repeat watching it. It's like something you have to memorize or get internalized. That is, you have to get it internalized. Some of the properties are to be internalized and connected with logical thoughts, other logical thoughts, so that it gets reinforced. ಮತ್ತೆ ಹೇಳ್ಕೊತಾ ಇದ್ರೆ ಅದು ವಾಪಸ್ ಗಟ್ಟಿ ಆಗ್ತಾ ಹೋಗುತ್ತೆ ಆ ತರ. So electron is spin half, neutrino is spin half, antineutrino is spin half. Now I add 3 spin halves. half plus half madi, angular momentum. What do you get? Angular momentum addition, half plus half. What is the value of angular momentum addition of 2 spin half? Half plus half. It's a simple question. You have to answer. Do you know what is half plus half? As a primary school kid, half plus half. Nobody is answering. What is this? 0.5 plus 0.5. What is the value?
1, ma'am.
But angular momentum, 0.5 plus 0.5. What is the value? 2 spin half particles, angular momentum. I have been saying this from day number 1. So I want your answer. Half plus half. Can it be
Zero.
minus 1? Can it be minus 1? Why are you so? Do you have a formula for angular momentum addition? I give you angular momentum J1 plus J2. What are the allowed values? If I ask you that question, what will you say? I'm asking you a simple example of that particular thing. Half plus half, angular momentum addition. You have a rule to follow. Tell me the answer.
Half and 1, ma'am.
Yeah,
Half, ma'am.
half and 1. Half plus half. What is the law, rule? Rule says, if J1 and J2 are 2 angular momenta, what does the rule say? What is the smallest value of angular momentum when you add J1 and J2? Smallest.
0, ma'am.
J1 and J2 is what I am asking. When I'm asking you one question, you shift to earlier question. J1 and J2 are angular momenta. What is the smallest value? Angular
Modulus
momentum.
J1 minus J2.
Modulus of J1 minus J2, because angular momentum J value is always positive. So if you write that, and I should ask you to give me a copy book and write J1 minus J2 is what are the values, and then half plus half, what is the value? Write it 100 times and submit it to me. It looks like that to me. So you should believe in angular momentum addition, which you have done the exercise. If not the whole exercise, remember the final result. Angular momentum addition gives you, if 2 spin halves are added, resulting spin is J1 minus J2, half minus half, that is 0, half plus half, that is 1, 0. And next step, in integral steps, you have to jump. These are rules. You have to write it in a copybook 100 times so that you don't make mistakes next time. Every minute when I ask a question, it should come straight. So now, half electron has spin off, neutrino has spin off, half plus half is either 0 or 1. 2 values are possible. Now, let us take 0, 1 value, and add another angular momentum. That is for neutrino bar, anti-neutrino. 0 plus half, anti-neutrino also has spin half. So 0 plus half, what is the allowed value? 0 plus half. Use the same rule. 0 plus half. What is the angular momentum of final particle? If you add spin 0 and spin half.
Half.
Half. No doubt about it. I'm asking you silly questions, but I want answers. So finally, it is going to be half if you add 0 plus half. But E minus and nu, half plus half had given you a 0 value and a 1 value also. 1 plus half. 1 plus half, what are the allowed values? Angular momentum.
Half and 3/2.
Okay. So it is half integral. Right hand side spin is also half integral, and it has a value half and 3/2. Right hand side spin. What is the left hand side spin?
Half.
Half. So it allows conservation of angular momentum. Now, if I had dropped the new bar, If I did not take a nu bar here, conservation of angular momentum would have given me E minus has half, nu has half, half plus half is integral 0 or 1. Left hand side is a spin half particle, but right hand side is a half integral spin. I would have got into that difficulty. So one knows that muon decay is a double neutrino decay. It has two neutrinos, one neutrino, one antineutrino. For one reason is that it has to conserve lepton number conservation has to hold, one thing. Second thing is angular momentum conservation should hold. It requires that I have to introduce two different neutrinos. So that is why I am just highlighting in a given process. You should, once you see the process, you should check what conservations do you know. Does it hold? In addition to what I am teaching today, you have to check that also. Now, I finished this. You understand what is left hand side spin, what is right hand side spin. If I have three particles, double neutrino along with an electron, this is a good decay. It is seen in nature. So now come back to the earlier one, top line. Mu pi minus gives you a mu minus plus a nu bar. What is angular momentum? We calculated lepton number. Do you know what is the spin of a pi minus? First, remember, what is pi minus? Is it a baryon? Is it a meson? Is it a lepton? I want answer for that. What is pi minus? Is it a baryon? Meson. It's a meson. Meson is a boson. So I will now ask you, a boson has spin, integral spin. It can be 0, 1, 2, etc. It can never be half. What is pion spin? Do you know that? So today I will tell you, you remember that and list all the particles that you know and classify them into baryons, mesons and leptons and write their spin values first. Okay, spin, angular momentum, so that you will remember. That is again another copybook assignment. You have to write it many times so that you will remember it. That is, these are known facts, experimental facts, but you should remember it. So how do you remember it? Write it several times. One copy you submit it to me. I will check whether you have done it properly. If you want to remember, if you want to know particle physics, properties, basic properties should be known. Pi minus has 0 spin. Okay. Now, what is spin of a muon? Mu minus?
Half.
Half. What is spin of a neutrino? Antineutrino, both.
Half.
So half plus half, angular momentum addition. What do you get?
0 and 1.
Okay. So left hand side is 0. Right hand side also gives you a possible value 0. So this process is a good process as far as angular momentum is concerned. So like that, I have to clear one by one. You tick lepton number conservation, give a right. Angular momentum conservation, give a right. It is like that. You have to verify. What am I talking now? I'm only talking about lepton number conservation. All these, what I have written here, conserve lepton number. According to what I said, left hand side lepton number is equal to right hand side lepton number. Having said that, I will now take, if I have asked for why a muon doesn't decay into an electron and a photon, why can't it happen? Because my known conservation laws can allow it. Muon is a heavy particle. It can decay into an electron and a photon. Are all conservation laws holding good? Charge holds good. Angular momentum. Left hand side is half integral. Right hand side is half integral. Again, I will ask you, what is the spin of a photon? I have asked many times.
1.
I have answered you. Now I want to check if you have learned it. What is spin of a photon?
1.
1. I have told you, so you should remember. You don't know it, but it's spin 1. Do you know electron spin is half? We have told you, you have believed it. We use that properties. So like that, photon has spin 1. So right hand side has 1 plus half, which can give you a half. So this process holds good as far as lepton number, as far as angular momentum, as far as charge, everything is possible. But one never finds a muon decaying into an electron and a photon. Even though the laws of conservations discussed so far, including lepton number conservation, they hold good for this process. So because this process does not happen, I find a new kind of a conservation law. I will say this is little subtle, but you have to give importance to it. The absence of this decay prompts people, that scientists saying that there is something called as a mu lepton number or electron lepton number. I have to make a sub classification of my particles and then say there is a muon is a lepton number different, electron as a lepton number different. Can I do that? In that case, how will I understand this particular process? I am repeating. When I say that lepton number is conserved, all these are fine, but I find one process doesn't happen in nature. This, even if I keep on searching for it, this has never happened in nature. So muon doesn't decay into a electron and a gamma photon. I don't find a photon in muon decay. Why it doesn't? Why is it not found? So I will say this could be because muon has some kind of what is called as mu-ness. I will say mu-ness for lepton number. So then I will introduce different families of lepton numbers. So please understand what I say appears like too many quantum numbers, but when I tell you why that quantum number has to be introduced, you have to remember that story. That is basic. And then I will check everything else and confirm that the new introduction makes sense to you. First, I introduce a mu quantum number, mu lepton number. What does that mean? We introduce electron lepton number. I will say electron lepton number Le is equal to 1 for all family of electron. And I will say electron comes with its neutrino. That is a pair, electron and neutrino belong to what is called as lepton number Le is equal to 1. Be careful. I am introducing a classification. No logic. Logic only is I am assigning it. I am giving it some name. Lepton number for electron lepton number is given a notation L suffix E that is equal to 1 for what? For only electron and its neutrino. So I denote electron neutrino by nu E now onwards. Electron comes with its own neutrino nu E. And muon lepton number L mu is 1 for the family of muon and its own neutrino nu mu. I introduce it. Why do I introduce it? I have to check examples. What is happening in nature and how does it happen in nature? All that is left in front of me. But I am now making a rule, Volt rule. That is, electron has a lepton number Le is equal to 1 and its neutrino denoted by nu E has lepton number 1. What is lepton number for a muon? I will say L mu, muonic lepton number. That is 1 for family of muon and its neutrino. What is the family? Family contains only 2 members, muon and its neutrino, electron and its neutrino. It's a family of 2. I call that as a family. I have to introduce what is so-called lepton number for electron separately, muon separately. That is the understanding. Today, I am just telling you why it had to be introduced. Muon cannot decay into an electron and a photon. So now I will say this doesn't happen because what is the muon lepton number for mu? It is +1. Mu minus L mu is +1. But what is L mu for electron? L mu, it's not a muon. So it is 0. So my rule now I will tell you Le is 1, L mu is 0. For what? I will write a lighter particle convention wise. Lepton family is denoted by electron lepton, nu E and E minus. For that, Le is equal to 1, L mu is equal to 0. Again, one more copybook assignment for you today. That is, you should know that lepton comes in a family, electron and its neutrino, they form a family, for which Le is equal to 1, L mu is equal to 0. Similarly, I have a nu mu and mu minus, for which Le is 0. This is not a electron. So I will say electron lepton number is 0. Muon lepton number is 1. This is an additional classification, additional feature that I am talking about. So what is Le for an that is anti-neutrino of electron variety? That is -1. But L mu is 0 for that too. So I write Le is 0 for a nu mu bar, and nu mu, mu plus has a L mu is equal to -1. This is the rule which we have to remember and follow when I talk about any process. That's what is the basic formulation, theoretical formulation. Does it work? We have to check it through examples and verify it experimentally. I hope you understand. I'm introducing a new rule. If I say 1 plus 1 is equal to 2, you learned it in your class earlier. First lesson in algebra, addition, subtraction and all that. Now I am telling you, there is a physics family called as lepton family. For the lepton family, I have Le is equal to 1. I write it, put that box and put all the electrons into it. And in addition, I put electron neutrinos also into that box. That is a family. So similarly, can I add a muon there? No, it is not an its electron lepton number is not 1. So I have to put different particles into different boxes. Then I will say electron and muon electron neutrino belong to one box, and muon neutrino, they belong to one box. Similarly, anti-electron neutrino and positron, they belong to Le is equal to -1 box, etc. So remember that and understand it. And then if you don't understand, raise a question, then I will be able to answer. Otherwise, I can't understand when I'm formulating a rule, why I formulate a rule and what happens next. That's what is my agenda. So I will say now, electron lepton, I'm again writing it. Electron lepton number is 0 for a muon and nu mu. And all the hadrons, photons, everything else other than a electron and an electron neutrino, they have Le is equal to 0. Le is 1 for an electron and electron neutrino. That's all. Otherwise, it is 0 for everything else. L mu is non-zero only for muon family. That is nu mu and mu minus. And corresponding anti-muon lepton family has L mu is equal to -1. Same thing holds for electron lepton number. Le is -1 only for nu e bar and E plus. So you have to make sure that that's what I am telling you here. Now I will say, with the introduction of conservation of lepton number in detail, for every sector, electron family, you have a lepton number. Muon family, you have a lepton number. Only for 2 particles, but it is important. Why it is important? Now consider what I call as a neutron beta decay. You know it, you have learned it. Now I have to add additional classification, that is a neutron decays into a proton plus an electron plus neutrino is what I said. Neutrino bar gives you lepton number conservation, as I told you earlier. Now you need to introduce nu e bar. Okay, earlier I said neutron decays into proton, electron and nu bar. Now that I learn that neutrino has to have a suffix, either e or mu, whatever comes there. So now let us check electron neutrino number, electron lepton number, left hand side lepton number. What lepton number? Electron lepton number. What is the lepton number of neutron? Electron lepton number of neutron. You have to answer me now. Is neutron, does neutron belong to a electron lepton family?
0, ma'am.
It is 0. Proton?
0, ma'am.
Electron?
1.
And nu bar. Now you have to ask, is this nu bar nu mu bar or nu e bar? If it is nu mu bar, what is the electron lepton number for a nu mu bar?
0, ma'am.
0. So, but it is a nu e bar, so it is going to be electron lepton number is
-1.
-1. So E minus has a +1, nu bar has a -1 for electron variety, so it is 0. So in the neutron decay, I have to be very careful now onwards because I have introduced a new concept called as electron lepton number, mu lepton number, etc. So here the correct process from now onwards till today, I'm not going to change it. So it is neutron going to a proton plus a electron plus a anti-neutrino electron variety. So now let us take pion decay. I told you earlier, pion decays into a mu minus plus a nu bar. Just one step earlier here. I was introducing lepton number here. Pi minus decays into a mu minus and nu bar. And I was arguing about lepton number conservation here. That is fine. But now you have to recognize what is electron, muon lepton number on left hand side. What is the muon lepton number on left hand side?
Zero.
Is pion a lepton? No, it is 0. What is muon lepton number of mu minus?
1.
1. And if I write nu bar, you have to tell me, is it a electron lepton or a muon lepton?
Muon lepton.
So I should write a nu mu bar for more clarity. I have to now on introduce, just nu doesn't make sense to me. I have to add a suffix. So I add a suffix there. That's what I do here. So I say a neutron here. Pion decays into a mu minus and nu mu bar, I should say. Because electron lepton number is also right hand side. What is the electron lepton number of right hand side?
0, ma'am.
0. So electron lepton number conservation holds. Muon lepton number conservation holds. Baryon number conservation holds. All that holds here. Now, same way, it is the crossing relation. This was fine. So now, what is muon decay into 2 neutrinos? One more decay is there. Mu minus. Earlier, I had told you there is a mu decay. Where is that? Earlier relation I had introduced here. Mu minus decays into a E minus plus a neutrino plus a antineutrino. Now let us assign lepton number on left hand side. I don't have a I scribe, so you have to write what is the L mu left hand side. L mu
1.
left hand side 1. L mu on right hand side for electron. L mu for electron
0.
0. So is there any L mu on right hand side? If it is not there, L mu left hand side and right hand side do not match. What should you put as a mu here? Neutrino should have a suffix mu. Left hand side lepton number is +1. Right hand side L mu should be 1. Which do you put a mu? A nu mu or nu mu bar. Which do you add a mu suffix?
Neutrino,
Yavudu?
ma'am.
Huh?
Neutrino, ma'am. For
A
new.
nu mu. Now,
New.
correct. This has to have a nu mu. I will show you the correct relation in a moment. Now, let us ask, what is the electron lepton number? Le, left hand side.
0.
And Le, right hand side.
1.
Electron has 1. But I have to have a 0, no? Left hand side has a 0, no? So Le is there, 1. I have to have a -1. For which do you write a
-1.
suffix? You will write a suffix nu mu bar,
Yeah.
nu E bar. So that's how I do it. So you have to learn that lesson of when does lepton family conserve lepton number conservation with the refined lepton number conservation. So if I write muon decay, I have to write a E minus and a nu E bar plus a nu mu. Then I will have L mu left hand side is 1. L mu, nu mu lepton number is 1. So I get 1 is equal to 1. Similarly, if I write Le, left hand side electron lepton number is 0. Electron lepton number here is 1. And nu E bar has -1. 1 minus 1 is 0. Similarly, I write for the rest of the processes. Now you tell me if whatever I asked you earlier, that is, one never finds muon decaying into a electron and a photon. What is muon number? L mu for left hand side. L for mu minus. What is the L mu? L mu
1.
means lepton number of muon variety. What is right left hand side? L mu gotta left hand side nalli. If at all I say mu minus decays into electron plus a photon. What is lepton number of mu minus L mu?
1.
1. Right hand side? L mu
0.
0. So it doesn't happen in nature. So I explained that mu minus giving you a electron and a photon never happens in nature. Done. So I can use lepton number conservation to rule out why some processes do not happen. Please remember that I have been emphasizing that lepton number conservation or any conservation law tells me in a laboratory, can I expect a process or not? I should have a, if that process does not happen, I should search for a conservation law, is what I learned from my elementary particle physics exercise. That is, in an elementary particle process, conservation laws are like God. You cannot violate it. If it is the process, then I should say, this happens because of this. It doesn't happen because of it. I should know that. So with that, I have introduced lepton number families now, and then you have to learn that. I give you some exercises. Okay. Now I will continue with, if at all I know that there are 2 lepton families, how do I check both leptons are different? That is nu mu and nu e are different. I have to do an experiment, because my theoretically I say that there is a neutrino for electron family, there is a neutrino for muon family. I have to do experimentally verify that. That is the next topic, experimental tests of 2 different types of neutrinos. That I will continue in the next class. When is my next class? If you please remind me half an hour earlier, I will try to get myself reminded and come send you a link. Okay. If I forget, because there are so many things